Okay, guys, today we're going to go a bit more in depth on the terms that we discussed before about current electricity. So, to be clear, there's a lot of different definitions you might find of current, and we'll go into that today. There's some that are conflicting, but the core definition that I like to use is current is the amount of charge that flows through a point in a circuit in a given amount of time. So we might say, okay, how much current is at this point in this circuit, and we could measure it by measuring the amount of charge moving through that point and the amount of time that we have. That's probably the most complicated, technical definition you get. So this is a slightly simpler one. And then I was kind of loopy, and it was late at night when I was writing this one. So this is like the simplest way to think about it. It's how much electricity or zappy zap goes through a wire at a certain amount of time. Important to note, this is not totally accurate. Because it doesn't have to be a wire to be a circuit, although we'll generally talk about wires. But this does help me remember it, so I don't know, maybe it'll help you remember it too. So conventional current is something I want to talk to you guys about because you might find this when you're looking in textbooks or online, and it's super confusing. I feel like people that have tried to describe this online or in a textbook did not do a great job. So bear with me. This is going to be the biggest hurdle. If you can get this, no problem. If you ever have questions about this, come talk to me. So there's a thing called conventional current. And when somebody says current, they're talking about that. So conventional current is the movement of positive charge. The weird thing about this is that when you've got a battery hooked up to a wire, which is one of the easiest ways to think about charge, your electrons are moving this way. They're moving from the negative part of the battery to the positive part of the battery. But the conventional current in the exact same wire is going the other direction. So electron current is the movement of electrons, and it's the movement of a negative charge. Conventional current is, since it's the movement of a positive charge, is in the opposite direction of electron flow in a wire circuit like this. So this seems like a crazy thing because we talk about wires a lot when we teach electricity and circuits and stuff. So it's weird to think that conventional current is used, but electrons are only one way that charge moves in the natural world, and it's only in like metal wires that's the way charge is transferred. There's a lot of other ways charges are transferred and moved throughout the world. So conventional current describes those generally, but also because we've got these different systems that have charge moving differently, we kind of needed to have one measurement that we call, okay, conventional current, it's our convention, we're going to say that this is the same for all types of circuits. So it was decided that we would have it going from positive to negative is the direction of conventional current. So Benjamin Franklin, I don't know if you recognize him. This is, I think, the guy who decided that this is what it was. Partially, they decided this that conventional current was positive to negative because they thought positive charges were flowing in a wire, but they were slightly incorrect about that at the time. But it doesn't really matter which way it was decided. The important part is that since currents move in different directions, it's useful to have a conventional current that we say, okay, this is always what we're going to compare it to. So again, I'm reiterating, current is always measured in the direction of positive to negative. And when we just say current, we mean conventional current. You can talk about the electron flow or the electron current, that's fine. But if somebody just says current, generally they're going to mean conventional current. So what is current? Current is measured in amperes. We already talked about this briefly, or amps for short. The symbol is A. And standard household stuff like 100-watt light bulbs have a current of about 1 amp. Important to note, amps is coulombs over seconds. It's a rate. And before we go into charge, I do want to note that you guys should try and understand conventional current. Do a bit of research if it helps you. Don't worry about it too much. And ask me questions if you're confused, because I know it's a confusing topic. We probably will have questions on it, and we will discuss it because I think it's important to know about. But once you get it, it makes a lot of sense. It's just it is kind of hard to have that switch flicked, excuse me. It took me a while because it felt like a lot of people were confused about it. So I think I was getting bad information as I was trying to learn more about it and try and break it down for you guys. So come talk to me if you're confused about that, or send me a message. So charge is the other thing we have to learn about um, for understanding current. And you guys should remember that charge can be positive or negative, and the charge of an electron is -1, and the charge of a proton is +1. I hope you remember that. I don't know. And we might think that charge only has to do with protons and electrons. And it's not quite true. Of course, those are going to be the baseline thing that are making everything else charged. But it's not always protons or electrons moving. So protons can flow through a wire like we showed here, right? We understand that, or sorry, not protons. We know electrons can flow through a wire, um, and that protons stay in the center, they're trapped in the nucleus. But that doesn't mean the nucleus and the entire atom can't move. And that's what happens in like a lithium ion battery. You've got lithium ions that are positively charged moving around, and those are creating a movement of charge. So oftentimes particles that carry a charge are what's actually moving, not just the electrons moving through atoms. And charge is quantified. Well, this guy is who it's named after, Coulomb. Charge is the unit for a charge is Coulomb, and 1 Coulomb represents the charge of this very large number of protons. This can be written as 6.25 times 10 to the 18. It's a lot. Remember, protons are very small, but that's still a lot. The Coulomb is very, very large. And I saw this example, I thought it was quite good. If you stood on a rug that had a Coulomb of charge on it, you would be slammed to the floor with a force equal to 1,000,000 tons. So, like if you put a Coulomb of charge onto the rug by like rubbing your feet on it, right? So a Coulomb of charge is a very large amount, and the reason we use it, like it's a pretty obtuse number. This is a kind of a silly number to use, or it seems like that at first. The reason it's used is that if you have a 1 amp current, you've got 1 Coulomb traveling through it per second. So this is kind of like a baseline measurement that defined what 1 Coulomb would be. And what is time? This is again one of the loopy things that I did late at night. It's seconds and minutes and stuff. In the formula we're going to be using for current, the really important thing to remember is that we're using seconds. So make sure to always convert to seconds when we use our formula for electrical current. Okay, that's it for the recap, guys. Again, conventional current is probably the new thing that is going to trip a lot of you up. Come talk to me. Cheers.